Good afternoon, everybody. Respected Honorable Vice Chancellor of the University, Dr. K.N. Kattimani sir, officers of the University, all the coordinators of the University. We are here in the afternoon session for 10 days webinar on role of nanotechnology in food and agriculture. So we have almost completed the 8 days. So today is the 8 days afternoon session. We have with us our none other than Dr. Dilip Rawat. So he has already explained you about the FTIR in his previous schedule on 22nd. He has explained. But today we have with us again same Dilip, Dr. Dilip. He is going to explain about Raman spectroscopy. So you know very well the importance and its applications of the Raman. There is a tremendous scope in Raman spectroscopy, and not only in the form of structural analysis, even we can do so many applications by using the Raman spectroscopy. And all those details is going to explain Dr. Dilip Rawat in maybe another 2-3 minutes. And before going to start the Dilip presentation, so I'll just go for a brief introduction because already we have known this introduction, but still some of the people may miss this introduction because he is one of the excellent specialist, application specialist in the field of FTIR or Raman or any kind of analytical, even a simple UV also he is having his own specialization. Dilip is basically a molecular spectroscopy and surface analysis working in the Thermo Fisher Scientific India Private Limited. So he has received his bachelor's degree in chemistry and master's degree in organic chemistry from University of Mumbai. He completed his PhD degree in organic chemistry from Shivaji University, Kolhapur, on synthesis and application of ionic liquids. He has done his postdoctoral studies from Korean Research Institute of Chemical Technology, South Korea, and Umeå University, Sweden. In his career of more than 11 years, he has worked in industries and academia under various capacities as a scientist, as a teacher, as an application specialist, so on. In his current role as a product application specialist, he visits customers for technical presentations and discussions, interactions, configurations, and also he has expertise in the field of infrared, Raman, UV, so on. His field of expertise is material characterization using vibrational spectroscopy. So as I just mentioned even in the previous day also on 22nd, Dr. Dilip is very vast experience in the field of spectroscopy, especially for spectroscopy last 12 years. Even he did his PhD also in some part of the spectroscopy areas, that is synthesis and application of ionic liquids. So even their busy schedule, we have requested Thermo for the, by having the different lectures or different application specialists in the field of Raman, FTIR, XPS, but all are really, they have readily accepted, and today again with us Dr. Dilip Rawat. So may I request Dr. Dilip for in the afternoon session in continuation. Dr. Dilip, please.
Yeah, so thank you very much. Thanks for the such a kind introduction. So very good afternoon to everyone. I hope that you and your families are safe in this pandemic situation and will continue to do so. With this, I will begin my today's session on Raman spectroscopy. Sir, can you see my presentation in presentation mode?
Yeah. It is okay. It's perfect. No problem. And before Dilip, before yeah, tell me.
Yes, sir.
Yeah, before starting for 1 minute, I'll take another minute from your end. It is very happen and very coincidence. Really, I was thank God to say that I'm just reminding. So today we have installed and demonstrated Raman spectroscopy in our lab, that too from the Thermo. Just I finished the demonstration in my lab, and I am attending now for in the online webinar. Same way, I am also attending for this in the morning. Yesterday they came and installed, demonstration completed in the morning, and again they are doing the demonstration. Thank you, Dilip.
Excellent.
Okay, yeah.
Thanks, sir. Thanks. Great to hear that news, sir. That installation has been completed.
Yeah.
Great. So, thank you very much. In today's session, I will be talking about the Raman spectroscopy. I will be going into the details of the basics of Raman spectroscopy. Then I will talk about the instrumentation of how the Raman instrumentation works. And then I will talk about some examples which are in which the Raman spectroscopy has been used, especially in for the food analysis. So, as I said earlier in on my lecture on Saturday, last Saturday, that the vibrational spectroscopy is basically there are two types of vibrational spectroscopy. The one is infrared spectroscopy. The other one is Raman spectroscopy. Similar to infrared spectroscopy, Raman spectroscopy can also be used for organic and inorganic material identification, whether they are solids or liquids, mainly for solids and liquids, whether the sample is in micro or macro form, it doesn't matter. It can be used for qualitative analysis and conformational analysis. And because of which Raman spectroscopy has been growing really fast in various fields. It has been used for identification of materials in catalyst and semiconductor industry. It has been used for polymer and packaging like food packaging as well. It has been used also been used for the understanding of the battery application, so how the battery works. It's especially when it's an charging is happening, in situ monitoring of that charging is possible with Raman spectroscopy. Gemstone and geology is another area in which Raman spectroscopy has been extensively used. Also, it has been used for carbon material identification, for its application, different layers. If it is from a single layer, multi-layer carbon material can be identified using Raman spectroscopy. It has been used also in pharmaceutical industries. So, for example, if you have like a tablet, and if you want to understand the composition of a tablet, you can use the Raman microscope to understand that composition and can make another tablet with a similar composition. It has been used also in life science applications for drug discoveries, for live cells, tissues, and I'll talk about one or two examples of this as well. It has been a very good tool in the forensic science, especially because it is a non-destructive technique and you don't need any sample preparation when you do the Raman spectroscopy. So it has been extensively used for many of the fields across a lot of fields because of its own advantages. Now let's begin with the basics of Raman spectroscopy. And it is, and we are very fortunate that C.V. Raman has discovered this Raman effect. After his name, they have, named this effect as a Raman effect, and for which he has received a Nobel Prize in 1930. So it was a story you can read in the reference that he was coming from London to India after attending a conference or a meeting, and while he was coming, and those days the sheeps they were basically coming. The transportation was sheeps. So when he was coming from London to India, he was seeing the water, and he thought that the reflection of the sky that I'm seeing in the water is not only the reflection. There's something different that is happening here. So once he landed, he did that experiment. So what he did was he tried to pass a sunlight through a filter, one of the filter, where he tried to interact one light, especially violet light, with the liquid, and then he tried to see what is the light which is scattered from that liquid. So he used another filter. He used the filters and then found out that the majority of light that has been transmitted was the scattered light, was a violet light, but there is something else. There's some other light is also been scattered, which is other than the violet light. And this is how he then did this experiment with various liquids, and then each liquid scattered light differently. So different light has been scattered. And this is how Raman effect has came into existence. Now, this Raman effect was also in a parallel period was being investigated in Russia. But C.V. Raman was the first one who has, who has published this result, and then he got a Nobel Prize for it. So it is also a story for the research students, that it is so important. Once you do the research, you have to publish it as fast as possible, to get the credit of your work. When I was talking about IR, infrared spectroscopy, the rule was the change in dipole moment. So here you can see when there's an asymmetric vibration, there is a change in the dipole moment, and IR light has been absorbed. However, when there is a symmetric vibration, then there is no change in the dipole moment, and it doesn't result in the absorption of IR light as far as the CO2 molecule is concerned. Well, so what happens in Raman spectroscopy? The Raman spectroscopy, as I said, it's a complement to IR spectroscopy, one which absorbs very strongly in IR, doesn't absorb much in Raman, and one, the vice versa. So what happens in Raman? Basically, when the when the light is hitting the sample, there are three things that occurs. First, the sample absorbs the light. Secondly, it scatters the light. And third, well, light just passes through. So for example, when the light hits the CO2 molecule, and when there is an you can see here, then when there is an asymmetric vibration, there is no change there is a change in the dipole moment, but there is no change in the polarization. And Raman effect is observed as IR. There is a change in dipole moment. Raman, it is all about change in polarizability. So you can see here, this was the original polarizability of the molecule. When there is when there is a symmetric stretching, where that means when the two atoms, oxygen atoms, are going away from the carbon, there is a change in the polarizability of the molecule. Similarly, when the two oxygen atoms are coming towards the carbon, you can see also there is a change in the polarizability, and this is what results in the Raman effect. So this is very important. And that this Raman effect is all about the change in the polarizability. It is associated with the polarizability of the molecule. So what really happens in Raman spectroscopy? So Raman, when the molecule is hitting the sample, as I said earlier, the Raman spectroscopy is also vibrational spectroscopy, similar to IR spectroscopy. That means there is a vibrational change when the light has been absorbed, or light has been when the molecule is interacted with the light. So the molecule goes from ground electronic state to the higher electronic state. Sorry, ground vibrational state to the high vibrational state. And similar to this happen in Raman spectroscopy as well. IR, it was all about absorption of this. This is caused by the absorption of the light, IR light. In Raman, what happens is when the molecule or the photon, laser photon, falls upon the sample, sample absorbs that photon and goes to a state, something called as virtual state. It absorbs that photon and goes to virtual state, and when it is relaxing, it comes directly to the electronic ground state. But the most of the light is coming to ground state with the release of the whole photon energy. However, some of the molecule or some of the energy is not released from the molecule, or it's what happens is it goes to, when it starts from V0, it goes to the virtual state. However, when it comes down, it releases the energy, it comes to the V1 electronic state. And this is similarly, this is what is called as a stroke scattering. While if the molecule, there are some of the molecules are in the V1 vibrational state, which can go to the virtual state, the higher vibration, higher state of the virtual state. And when they come down, they come directly to the V0 ground state. And that is what we called as anti-stroke scattering, by which you can see here there is an absorption of energy that occurs in the molecule, and molecule goes from V0 vibrational state to the V1 vibrational state. This is what causes the Raman effect. The laser light falls upon the molecule, the light gets scattered. The most of the light which gets scattered is known as Rayleigh scattering, and 1 out of the million times So the light which is scattered where there is when it goes to the V1 ground state, the mostly you see a Stokes scattering, while there is also an anti-Stokes Raman scattering also observed. So basically, what you see in the Raman spectroscopy, when you see a Raman spectrum, you normally see a spectrum of intensity versus Raman shift. It is not the intensity versus the wave number. What we are seeing is we are giving a light, a laser light, a monochromatic light on the molecule, and then it absorbs, or it results into absorption of light and going from V0 to V1 state, giving you a particular peak, particular absorption. And what we see in the Raman is this difference, and that is why it is called as Raman shift. We see the Raman spectrum as the intensity of the absorption versus, or intensity of the scattered light versus the Raman shift. So, as far as the Raman effect is concerned, as I said, it is all about change in the polarization. And therefore, the molecules like nitrogen, which I said was not absorbing in the IR region because there is no change in dipole moment, it absorbs in the Raman, it absorbs due to the Raman effect. And it shows a peak in the Raman spectrum. Well, just to compare an FTIR and Raman spectrum of benzene. Now, benzene typically shows different peaks in the FTIR region. So you can see here these kind of vibrations when there is a change in the dipole moment happens in the ring when this hydrogen is coming inward and this stage is going inside. This is outside. You can see these are the vibrations which are causing change in the dipole moment, and it is absorbing in our region. While this one, the one which is not so strong here, which is the symmetric stretching, you can see here it results into the Raman spectrum. So that is how it is complementary. The information that is missing in the infrared spectroscopy, that information you can get in your Raman spectrum. It is the ring flex modes have been seen in the infrared spectroscopy. It absorbs in the infrared region, while the ring breathing, like that is like the all carbon molecules are going inside and then they're coming outside, kind of a breathing effect. That ring breathing you can see in the Raman. You see a peak at around 1000 centimeter inverse in the Raman spectroscopy, which also confirms the ring structure of benzene. So this is how infrared spectroscopy and Raman spectroscopy can be used as a complementary tool to get more information of your molecule. But sometimes what happens is you're running a spectrum and then, oh, I cannot see my spectrum. So there is something else that is also happening during the light or a monochromatic light that falls upon the sample. And that is what is known as fluorescence. Now, fluorescence is a killer to a Raman spectroscopy. If a molecule fluoresces, well, it fluoresces, and then you don't see Raman peaks. The Raman effect is a very weak effect. 1 out of 1,000,000 times it shows a Raman scattering. However, fluorescence happens when it happens. It is like one out of 100 times. So therefore, when light falls upon the samples, what happens in fluorescence basically is that when the light falls upon the sample and is scattered, the molecule directly goes from an electronic ground state to the rather than going to the virtual state, it goes to the electronic higher state. And then it comes down, and then when it is coming from V0, so it comes along the vibrational levels of higher electronic state, and then when it comes to the V0 electronic state, it directly goes to the higher vibrational state of the ground electronic state, and that is what is causing the fluorescence. And this is really the as I said, is the killer to the Raman effect. So typically what you do, you try to have a laser light. So if in order to have in order to avoid this, what you can do is you choose a laser light whereby which this does not occur while it goes to the virtual state and come back to the vibrational state, giving you that Stokes Raman scattering, and you can see the Raman spectrum of your compound. And how we can do it, I will explain in my next slides. Well, what kind of information you get it from Raman? Now, as I said, Raman spectroscopy can be similar to IR spectroscopy, can be used for molecular identification as well as the quantification. But there is something more also Raman gives you. Raman can be used for polymer identification, which is one of the important application of Raman. For example, if the TiO2 exists in rutile as well as anatase form, and it shows a different frequencies for rutile as well as anatase form. So from characteristic frequency that you see from Raman spectra, you can identify the material as well as you can identify what kind of polymorph that is present of that material. From the intensity of the peak, you can understand the quantity of the material. That means you can do the quantification of your material using Raman spectroscopy as well. Raman spectroscopy is susceptible, or it is very much sensitive to the change in the physical properties of the molecule. For example, if there is a stress and strain in the material, then you will see a shift or a change in the frequency in the Raman shift. So for example, you see a 520 centimeter inverse peak shift in silicon when it undergoes a strain. Similarly, there is a change in the width. The molecule you can see a Raman peak width increasing, which shows that there is a disorder or a defect that is present in your molecule. So, for example, a crystalline molecule, crystalline silicon shows at 520, while the amorphous silicon absorbed at around 480 centimeter inverse. Similarly, the defects, when you have a carbon material like graphene, it shows the defect was identified by a band called D band. Otherwise, it has 2D and G band. So this is how you see the change in the word, and this can be even helpful to get the information of disorder or defect in the molecule. The change in the frequencies, the change in the intensities, and the change in the width, if you see all those things, then you're actually seeing the effect of either a thermal or a pressure impact on the molecule. So what you're seeing actually is the physical change, the phase transformation or the melting that is happening, or crystallization if that is happening. You will see there's a change in the frequencies, intensity, as well as the width in the Raman spectrum of that particular molecule. Also, if you use a polarized light, yes, similar to IR, infrared spectroscopy, you can use it for understanding the symmetry or orientation of your structure. So this, for example, if the molecule is oriented, or a particular group, sorry, in the molecule is oriented at different angles, then you can use, if you use a polarized light, you can see that the intensity of that particular peak will be of that particular group will be varying depending on how is the orientation of that particular group. For example, in a polymeric structure, you can correlate that with using the Raman spectroscopy. So this is what kind of an information you can get from the Raman spectroscopy, and that is why it is such a good tool for the molecular identification, the material and structural identification. So just to give you an overview of Raman spectroscopy is associated with polarizability change. So there is a change in the electron cloud, and it is sensitive to the vibrational modes of covalent bonds in the molecule. So covalent bonds, which are very similar, have very similar atoms, and which does not does not have absorption much in the IR region. That can be seen in the in the Raman spectroscopy. Peak occurs similar to IR at the specific frequencies. They are more sensitive to the highly symmetrical vibrations. For example, if you have a polymeric chain, which is CH kind of a bond, and this bands you will see in a very intense band you will see in the Raman spectroscopy. It is polarization dependence, and you can see also the multiple, you can use it for identification, quantification, also the kinetic studies, as I said, talk about the lithium battery application. You can also, you can do the kinetic studies. So just to give you a difference or how the FTIR and Raman spectroscopy is all about. The FTIR is all about absorption spectroscopy. Molecule absorbs the light and transmitted light goes towards the detector. You see an FTIR spectrum. In case of Raman, it is all about scattering. The light falls upon the sample, the molecule scatters the light, and what you see is that scattered light that you measure. FTIR associated with the change in the dipole moment, Raman, change in the polarizability. End group provides, for example, polymeric chain, if you're looking at, then the end group like cyno group or say CHO group, these groups shows an intense signal in FTIR, while the backbones like CH the arrangement, you will see an intense signal in Raman. Strong signals for polar functional groups, strong signals for delocalized electrons. In the FTIR, you have to use the non-IR absorbing windows like KBR, zinc selenide, etc. Kind of windows you have to use. While in Raman, you have to use glass, or you can use glass and plastic as well. So there is some kind of a sample preparation that is needed when you do the FTIR for some of the accessories. While in case of Raman, you most of the time you need no sample preparation, or if it is needed, very little sample preparation is needed. The advantage of FTIR is that you can simultaneously view and collect. So if you're doing it under a microscopy, you can view the sample as well as you can collect the infrared spectrum. In case of Raman, however, you view the sample and then start collection, because the laser is harmful to your eyes. So whenever you're working with Raman spectrophotometer, if it is not open, so if it is not closed, if it is an open kind of a system, you have to use the goggles for protection. The transmission, reflection, in ATR mode, Raman can be basically scattering of the samples. So there are some benefits that are offered by Raman. It gives, as I said, it's a complementary information that you get, but it gives you the symmetric bond, like SS bond, CC bond, and more information you get of the molecular backbone for the Raman. Another important benefit that Raman offers is that it gives you a typical spectrum up to 50 centimeter inverse, which is like from 3,500 up to 50 centimeter inverse. So if you consider IR, you are considering the range from 4,000 to 400 centimeter inverse, which is a mid-IR range, while from 400 to 50 centimeter inverse, you're talking about the far IR range. So Raman covers the entire range of mid-IR as well as far IR. So it's a very good tool for what we use for inorganic molecules, which we see absorption in far IR region. Many of the inorganic compounds absorb nicely in the Raman spectrum. And atmospheric water vapors, which is a concern in the Raman. That's why you have to take, in the infrared spectroscopy. That's why you have to take the background. But well, something which is creating, which is strongly IR absorbing. Well, there's no problem for Raman. So atmospheric vapor, water vapor is not a problem for the Raman, because water absorbs very little in Raman spectroscopy. Another important thing that offered by the Raman is that it's a non-contact technique, it's a reflection technique, and therefore the sample geometry does not matter much. So even if it is an uneven surface, well, you can use Raman spectroscopy. It gives you a very good spectra nearly on any substrate, whether it's metal, whether it's glass, paper, polymer, silicon. Well, it gives you a very good spectra. You can do as I said, no sample preparation is needed. So you can directly have a sample analysis, need sample analysis. Take the tablet, put it under the Raman in the Raman instrument, and you do the analysis. Just measure the raw sample, and you get the results. Another important advantage of Raman is because the laser light can penetrate deeply, and you can have a confocal Raman spectroscopy, spectrometer, and therefore, even if your sample is in glass or in a plastic packaging, well, there's no problem. You just don't have to open it. Just do the analysis even in glass. So, like what you want, if you want to check what is there in the bottle, well, you keep a bottle and do the analysis of your sample. So this is the kind of advantages that Raman Raman offers. Another thing important is that the spectral subtractions are very clean. In Raman, the reason behind this, the Raman is basically for the backbones, and therefore it has less absorptions in the polar groups. which actually have the results into the hydrogen kind of bonding. So it has an effect on those kind of peaks. If you change the environment of your for your solvent, the change of solvent has an effect on the absorption spectra in infrared spectroscopy. Well, in the Raman, the what we are seeing actually are the bonds which are like a covalent bonds, CC bonds, where there is not much effect of the solvent or the environment on those groups, and therefore there's a very clean spectral subtraction you see in the Raman spectroscopy. So these are the various advantages that Raman spectroscopy offers. Now, that means that doesn't mean the IR is better, or or some IR is better or Raman is better. Both are the techniques which have their own advantages, and it's a complementary information that they give. You use the both information and get the more data of or more information about yourself. So with this basics of Raman spectroscopy, I will go through the instrumentation of Raman spectroscopy. Raman spectroscopy, as I said, Raman, it's a non-invasive technique. You can couple the Raman with the microscope. No sample preparation. Another important advantage of Raman that it has a very high spatial resolution. You can go up to 0.5 microns using Raman, and it has high sensitivity to inorganic compounds. So as a thermofisher, we offer different types of Raman spectrometer. One is the DXR3 Raman microscope, which has the capability of point and shoot as well as the mapping, so you can have a mapping of your sample. DXR3 imaging microscope, so it's the same microscope with the where you can do the analysis more faster. One of the another important instrument is the DXR3 Smart Raman, which is used for the bulk sampling. So when you have, as I said earlier, also when you have a micro samples, you need to use the microscope. While when you have macro sample, well, you can straight away, you don't need a microscope, and you can have a bulk sampling analysis of your sample using instrument like DXR3 Smart Raman. Also, another important, tool in the Raman is the FT Raman. Now here you can see our IS50 IR instrument, in which you can put this FT Raman module and do the analysis of both. You can do the analysis of your IR analysis, and when you put the module in, you can do the Raman analysis and have both the analysis in the same instrument. So this is how you can. These are the different types of instruments that are used for different purposes when you are using a Raman spectroscopy. So first, I will talk about. I have spoken about the FT Raman in my presentation during an IR. So today I will be basically talking about the dispersive confocal Raman spectrometer. So basically what you see, the Raman spectrometers are the dispersive Raman spectrometers, and there are a few important components. Key components of Raman spectrometers are laser. A laser light, which gives you the laser, it gives you the light that falls upon your sample, and then there's another important key component is grating, and finally there is a detector. It also uses a filter to filter the Rayleigh scattering, because that is the maximum light that has been scattered from the sample. So you have to use a filter. So the filter is very specific. So the particular laser will have a particular filter. So this is how it works. The laser light falls upon the sample. Samples then scatters the light. That light has been then passed through the filter. Whatever is the Stokes light are then falls upon the grating where the resolution occur, and then it falls upon the detector, and finally you get the Raman spectrum as the Raman intensity versus the Raman shift. So let's begin with the first component, that is the laser. There are different lasers have been offered with the instrument. For example, 455 nanometer laser, 532 nanometer laser, 633, 785, 1064 nanometer lasers. Now you can see here the laser, different lights have been offered. This is the reason behind it is it doesn't matter which laser you use. The the spectrum that you the spectrum of the compound is not laser specific. You always get the same peaks, whether you use 455, 532, 785, or 1064 nanometer lasers. Why you have to choose the different lasers is the reason, as I said, fluorescence is the problem in Raman. Fluorescence competes with the photons, and the fluorescence is more predominant than the Raman effect. The longer the wavelength, that means once you go from 455 towards 1064, the longer the wavelength of the light, less is the fluorescence. So if your molecule is fluorescing, then you go towards you choose the longer wavelength lasers. However, there is another another challenge that if you go toward the longer wavelength of the lasers, the Raman efficiency decreases. Raman efficiency is directly proportional to 1 by lambda raised to 4. So Raman efficiency is inversely proportional to the wavelength of the laser light. So it's always a trade-off. So if the molecule doesn't have a fluorescence, well, you can go nicely with 532 nanometer laser. If it fluoresces, well, then you can use the 785 nanometer laser and get the same information, but you will get the lesser intensity of that particular peak. So this is a kind of trade, and it depends. It varies from sample to sample. So this is how you choose different lasers. So different applications, you have different lasers to use. As I said earlier, different excitation lasers gives the same Raman spectra. The Raman peak position is independent of the wavelength. It's only that the fluorescence that decides what kind of laser you are going to use. If it fluoresces, well, you have to go to the higher wavelength lasers. Well, the second important part, as I said, is the grading. So once the laser light falls upon the sample, the scattered light from the sample then goes towards the goes through the filter, then comes to the grading, where this light has been resolved, and finally, it resolves into different wavelengths, and then what you see and then it falls upon the detector to give you the spectrum. So this is there is the standard resolution grading. So the gratings are laser specific. Mostly you want to use the optimized gratings for particular laser, so that it covers the entire. So what the thing is, the detector size is fixed. So you have to use a grading in such a way that the entire range from the range that you're looking for, it covers into that length of the detector. And therefore, the more optimized gradings you use, the laser specific gradings you use, better results you get when you're doing the Raman analysis. If you want to have a higher resolution grading, if you want to see a higher resolution, what you do is you change it with the higher resolution grading, and then you cover the area with the higher resolution and get more resolution across a particular area. So you can have resolution from say 50 to 1800 centimeter inverse. Higher resolution you can get with the higher resolution grading. Grating basically it's material. It's a very flat, shiny material where there are grooves upon which the light falls, and the laser light, the scatter light falls upon and then resolved into different wavelengths. The detectors that are used in Raman spectroscopy basically is a CCD detector. The EMCCD detector is used when you're using an imaging technology. So if you want to do very fast analysis, well, then you use the EMCCD detector, while otherwise you use CCD detector. There are certain different types of illuminations, front illumination, back illumination. Depending on what kind of application you work with, you choose the front illumination and back. As I said, it's Raman has been a very good technique for depth profiling. You can get the 2 micron spatial resolution in Z direction using the Raman. So you can choose the point. You can focus the laser light at a particular layer in your sample and do the analysis. So you can see here, you focus on this area and you can get the spectrum of this depth or this layer of your sample. If you change the depth, or if you focus the laser here, then you see if you move up, then you can see now you see the red layer. So this is how you can move the sample in Z direction and have the confocal or the depth profiling of your sample. So this is how you can do the analysis. So here is the green one. You can see the upper layer. If you go down, you can see the red layer, and then you go down. You can see the you can analyze the blue layer in your sample. Now I'll talk about the DXR Raman microscope. This is the microscope that we offer. It's a confocal Raman spectrometer. It's a very compact design, a very small footprint design. Importantly, it's a class 1 laser safe enclosure. So you put the sample inside, you close that sample compartment, and then and only then, once you close it, then the laser starts and you can start the analysis. So first what you do, you put the sample in, you see where where you want to do the analysis, you close it, or you can just keep the sample inside, close it, and on the computer you can change where you want to see. You can see the region and do the analysis. Here you don't require goggles, say laser safety goggles, because of this class 1 laser, class 1 laser safe enclosure that comes along with DXR Raman microscope. Another important feature is that it has an integrated component. That means the laser is user replaceable. You can just put one laser, specific filters, and then you put the specific gradings, which are very specific to that laser, gives you that optimal result or the best performance for your Raman spectroscopy. It comes with a research class optics as well as microscope, so you can have a binocular and a digital camera for sample viewing, and then once you view it, identify the area, identify the sample location, you can do the analysis, and then it has the stage on which you put the sample and have a CCD detector. So these are the components: smart lasers, gradings, and filters. It has been automatically recognized by the software. So once you insert a particular laser and a laser specific grading and the filter, it has been automatically recognized by the software that now, yes, you have put in the 785 or you have put in the 532 laser. So you don't have to even put anything inside once you know that, okay, you have to mention, it doesn't have to mention which kind of a laser has been placed in. Very smart log technology. So you just have everything what you do when you put laser in or when you put the grating in, it just you easily can do the fitting and it fits in very nicely inside, and then there's nothing, no misalignment possible in this kind of a triplet, what we call triplet spectrograph, where there are no moving parts. Normally what happens is if there is a mechanical moving part for changing, say, gradings or for changing filters, then it can cause there can be some problem with the mechanical changing can happen, and then there can be a downtown in your instrument, which that is why we have come up with this technology. It has an automated alignment and calibration, so you can use this. There's a calibration tool. You just put it under the microscope, click of a button, just click here, auto align. Well, then it does the alignment and calibration for you. Completely automatic calibration. Just have to put this tool under the microscope. Well, another important feature of the DXR Raman spectrophotometer is the laser power regulator. It controls or it compensates the changes of laser power output. So what happens in the DXR Raman is that normally what happens is over a period of time, the laser light and the use of the instrument, use of the laser light falls, it goes down and down over a period of time. But when you're doing an analysis, you always want the same amount of light to fall upon the sample for a particular sample. So if you're doing an analysis for your sample with a particular amount of laser light to get your result, next time, after say even after a year, you want the same amount to fall upon your sample so that you can get the consistent result. And that is possible when you have a laser power regulator, which regulates the power on your sample or the laser power that falls upon your sample independent of what is the laser output is. So this is how it ensures that the same amount of laser light every time falls upon your sample, where it is today or even after a year. It will give you, say if it is say 5.1 milliwatt you want to put on your sample for analysis, every time it will allow you to have that same laser power on your sample. It's a very good feature that DXR Raman offers. Well, it has a versatility, expandability, and upgradability. All these lasers, everything is user replaceable. So today, if you have a 532 and 785 nanometer laser, and you want to have say 633 nanometer laser, next time you buy it, well, you don't need an engineer or someone. You just do it by yourself. You just plug in 633, put the laser, put the grading, well, good to go for analysis. And so this is the way this design have been developed in order to have that expandability of the Raman technology. Well, this was all about the instrumentation. I also want to talk about one of the feature or the spectroscopy technique that we use along with with using the Raman spectroscopy, which this surface enhanced Raman spectroscopy. This has been used for food technology a lot. So if you refer the papers, research papers in food technology, you will see the SIRS or surface enhanced Raman spectroscopy most widely used. So what is a surface enhanced Raman spectroscopy? As I said earlier, Raman is a very weak effect. It happens 1 out of 1 million times. And therefore, the surface sensitive technique, this SIRS, surface enhanced Raman spectroscopy technique, enhances the Raman scattering by the molecule. What they do is that they have the adsorption of the molecule on the metal surfaces or the metal nanoparticles, because of which their interaction, it results in the enhancement in the signal of Raman by about 10 to the power 10 or 10 to the power 11 times. And it gives, even if there is a one molecule, it can give you a strong signal in Raman. So because when you're looking at the food technology, you're looking at very small components, like if you want to see some foreign particles or say pesticides in your molecule, then they are in a very small amount, but you want to detect because they are very detrimental to the human life, even in the small concentration. So what typically happens is that when the molecule is put with these colloids, silver, gold, or copper colloids, it interacts with them. The laser light, when falls upon it, it gives you that surface enhanced Raman signal, and you can see a very strong signals of the molecule in the Raman spectroscopy. So this is, it's just to use and use, you have to use this colloids. The shape and size of these metal nanoparticles affects the strength of the enhancement. So how much it will be enhanced, it depends on what kind of nanoparticles you're using, and in general the surface roughness or the nanoparticle size correlates with the excitation for the maximum enhancement. So you have to see which one gives you the best results. So it's chemically, it is the formation of charge transfer complex of the molecule with the metal nanoparticle that gives you that more scattering of from the molecule and gives you the signal. Well, with this, I would now start with the Raman application. Well, Raman has been, as I just want to reiterate why Raman has been used, because the identification via spectra is similar to FTIR. You can do the analysis from bulk level to the micron levels using the microscope. No sample preparation, great for inorganic material, as the water absorbs very little in the Raman. This is a very good technique for aqueous samples or biological samples. You can do the depth profiling as well as you can the sample can be analyzed even through containers like glass containers or say plastic containers. So a no-touch sampling, very good for forensic technique, forensic material as well. In terms of food analysis, Raman spectroscopy has been used in a variety of application. For example, for understanding the food components like protein, carbohydrate, lipids, vitamins, and minerals can be identified using Raman spectroscopy. Microorganism and viruses can be identified using a Raman spectroscopy. And I saw one of the paper published where they have did the study to understand the viruses, and they were extrapolating to so that this can be used maybe later on for COVID-like identification, because it's a non-destructive technique. You don't have to do those PCRs and the other things which is an extensively and which are extensive processing, as well as the economically it is very costly. So Raman maybe in the future will be a very good technique for this kind of analysis. Raman can also be used for understanding the food adulteration. It can be used for understanding what are the additives that are there in foods. Toxin or chemicals like pesticides you can identify using Raman spectroscopy. And as I said, it can be used for bulk material identification as well. So there are three techniques that are used for food analysis in Raman. Using Raman is you can use a dispersive Raman spectroscopy like DXR Raman, or you can use the Fourier transform Raman spectroscopy, which I showed, that is FT Raman, along with IS50 FTIR spectrometer, and you can use the surface enhanced Raman spectroscopy for doing your analysis of your sample. Now, this is the first example I have chosen as far as the food is concerned. Now, this is the nanosilica, just a moment, nanosilica carbon silver ternary hybrid for food packaging. So basically, there is a high demand of high quality and safe food products, along with the development of biodegradable coatings or fillers for putting this food material. And what they want was they were in this study they wanted to have the microbial activity to have that property should have for that food packaging. And that is why they made a silver bio-based from the from the rice husk. They have prepared these silver nanoparticles using a ball milling technique, and these materials were then incorporated into a viscous biopolymer to fabricate this antimicrobial thin film. So they wanted to study how that material has been formed, how is the interaction of the silver nanoparticles along with the material. All this study they could possibly do using Raman spectroscopy. So, for example, here you can see the silicon carbon silver nanoparticles absorbed at around 1430 and 1500 sorry 1200 and 15 1200 and around 1700 it absorbs, while when you see the when it is interacted with the molecule called ecoflex, you can see there ecoflex absorbed at around these two frequencies at around 1700 and 785 or and 720, and there are some bands at around at around some 1600 and 1618. So these two bands, you can see when there is an interaction, or when there is when the silver nanoparticles have been incorporated in that material, you can see that there is a shift, a continuous shift from 3 to 9 centimeter inverse shift of these peaks. You can see all the peaks where there's a peak here of ecoflex. All the peaks with the increasing concentration of nanoparticles have been shifted. So you can use this to understand that this is due to the interaction of silver carbon nanoparticles with the blended composite that is being used in order to form that film. So this is how the Raman spectroscopy can be used to understand how is the interaction of materials with that of the that of the system. However, there is no strong interaction, or there is no new peak that has been appeared when you do this Raman analysis of different concentration of samples, which indicate that there is no a chemical bond, a new chemical bond is formed. Rather, it's just an interaction, or the blend, or just it's the incorporation of the nanoparticles in the material is happening during this formation of this film. Well, for the details, you can go through these references which are mentioned at the bottom of this slide. There's another interaction of nanoparticles with polymethoxy flavones. Now, basically, TiO2 has been widely used as a food additive. Sir, can you hear me? Sir?
Yeah, Dilip, you can go ahead.
Good. Because it just showed me that my internet is weak, so that's why.
No,
okay. So I'm loud and clear, right? So,
yeah.
Yeah. Good. There's another study wherein which they have done the interaction of TiO2 with this polymethoxy flavones, which are used for in the food material. The TiO2 is basically used as a food additives for many of the components like chewing gums or candies and other sweet material. However, some of the research papers have indicated that TiO2 has a potential adverse health effect of oxidative stress, inflammation, damage to liver, kidneys, and spleen. Now, what they have observed is that when you add TiO2 along with other flavonoids, then it reduces the damage, reduces the inflammatory effect, as well as the renal damage caused by the TiO2 material that is there in that food material. This is, but what they wanted to study was how is the interaction. So what it is causing that reduction of the adverse effect of TiO2 because of the presence of these flavonoids. That is why they did that study. What they have done is they mixed with these different types of flavonoids like DDN, and there's a structure here, as well as there's another flavonoid like TDN. They mix it with TiO2 in order to understand how TiO2 material has been interacting with these flavonoids. So basically what happens is TiO2, when it is a nanomaterial form, the surface of that nanomaterial is exposed. And when as you know that when you have a nanoparticles, always there are these valence bands, or the vacant, or what they called it as, it is always unfilled. The upper layer has the unfilled electronic states of the upper layer molecules, and these molecules interacts with the other organic molecules and try to satisfy their to get the good coordination. This is what they were trying to study. So you can see here, if you look at the peaks like DDN, these peaks like 1655 is a peak of carbonyl in this C ring, while this 1564 is the peak that in the Raman is associated with this double bond. While this 1360 shows is the ring, aromatic ring flexing, that interaction or vibration at 1360, while 1315 is the aromatic absorption, or the aromatic absorption in the Raman spectrum for this DDN molecule. Now, when they have put or mixed with TiO2, what they have seen is there's no much change in these bands. Like there's no change in the carbonyl frequency, there's no change in this frequency with the double bond that is attached. Rather, there's no change, also much change in the frequency of this aromatic ring. But what they have seen is that there is a large shift, almost a 10 centimeter inverse shift of this band, or this peak in the Raman, which is associated with this ring. So this indicates that the TiO2 material that is there is actually interacting with these two OHs, or this benzene ring with these two OHs, and getting stabilized, and because of which it is showing that reduction in its effect, or adverse effect that it has. So this is how that molecule is making it more less adverse by interacting with this ring. Similarly, you can see here this TDN molecule, which has the absorption at around 1602. All these absorption doesn't change when TiO2 is added. Rather, this 1316, which is similar benzene, when it interacts with the TiO2 molecule and have the interaction and the coordination with this part of the molecule has been shown. So this is how Raman spectroscopy can be used in order to understand the interaction of TiO2 nanoparticles with different kind of organic molecules. It's a very good study to see how see something you see that okay, there is a change, there is a reduction in the damage due to some material, but why, how? This is how this gives you a proof of how it is working along with the TiO2 nanoparticles. Another example is the where Raman spectroscopy or surface enhanced Raman spectroscopy is used to detection of foreign particles in foreign proteins in the milk. It's normally cross contamination of foreign allergic proteins in food products due to the not good processing from the factory, can lead to having different types of materials or different types of products in your food, which can be allergic for certain kind of humans or the animals. These are the foreign, what they call as foreign proteins that have been found in the milk, which can be allergic to some. Currently, the techniques that are used are like ELISA technique, the enzyme link immunosorbent assay, or they do it with chromatography with different detectors. And these techniques are very expensive techniques, time-consuming and labor-intensive technique. Raman, on the other hand, as I said, well, you don't need sample preparation. So here is what they have done. They have taken a sample they have taken the silver, dendroids, and they try to have that particular protein which they want to see, that particular protein has been put it on this silver dendroid. Then it has this OVA, that is ovalbumin, is what they wanted to see. So this is they have put the capture the anti OVA, and finally, and then they have taken the spectra of that particular compound, and finally they have captured the targeted material and see what is the effect. So you can see here, you can see the study here. This is the silver nanoparticles that has been formed. This silver dendrites are formed from nitrite, nitrite solution. So you can see an NO3 stretching in these samples. Now, once it start interacting, so once it reacts with that protein, you see there is no change. There is no there's no NO3 peak you are seeing here. So there is a change in the spectra that is observed, indicating that there is an interaction of the silver nanoparticles, which we use for surface enhanced Raman spectroscopy, and it is now showing the spectrum of your protein. Now, once this protein material has been interacted with anti-OVA, that is the binding of anti-OVA, it has shown a spectrum, a different spectrum. While when it has captured the OVA, it has resulted in a different spectrum. Now, in the normal first order spectrum, there is not much of the it shows a different peaks, however, not that much distinguishable peaks. So what you do a secondary derivative of your spectra, and now you can see the actual variation in the peak. So the peak, one which you see in silver G anti-OVA, is the peak which disappears here when the OVA is incorporated, and now you can see this peak has been enhanced. So this is how this technique can be used for the identification of foreign protein. So you can use it for any other protein by doing this quantification. So once you have a quantification model that has been derived using this spectrums, once you have quantification models, well, then you can take the spectrum and just predict what kind of concentration of the foreign protein is there, and whether it is there or not, whether yes or no. It's a good technique for saying this material or this foreign protein is there in the milk or not. So this is how the Raman spectroscopy along with the surface enhanced technique can be used for detection of foreign proteins in the milk. Another example is detection of pesticide like fipronil. In the eggshell and in the eggshell and the liquid eggs. Now, this fipronil was been there was one of the studies, or one of the it has been published that there is a poisonous egg scandal that has been seen in Europe, where they have found the substance, a pesticide called fipronil on the surface of the eggs. And then they have to ban the batches of all these eggs, and resulted in the economic losses, and also causes a risk to the public health. So in order to detect this pesticide, whether that is present or not on the eggshell, they have used a simple method. Fipronil basically, when it dissolves in acetone, and when you put the water in that one, 6 times the water in that solution, it just precipitate as a crystal, and then these crystals you can see the spectrum under the round photometer, and you can identify the fipronil. Even when in order to identify the eggshells, what they do is that they take a swab. They put the swab dip into acetone, and then they put that swab in the solution, and finally they take the Raman spectrum. So you can see here the calibration curve has been derived. So they have taken the spectrum with different concentrations of the fipronil, and then from this peak they have derived the calibration curve. And now just taking a swab, put it in the water, looking the crystals, and you can understand whether the fipronil is present, and if it is present, in what quantity it is present on the shell of the egg. Also, you can do the similar thing with the egg liquid as well. So if it is there, you can do the similar process, and finally you can see these crystals under the Raman microscope, and you can do the analysis and understand what kind of percentage of fipronil is there in the liquid eggs as well. Another example of these were the examples where you have a small quantity of the material, and you have to use the DXR Raman microscope. So if you go through this these literatures, you will find that the DXR Raman microscope has been used for these kind of analysis. Other technique, as I said, FT Raman is also a very good technique to understand the composition of your material. If it is present in the bulk, well, you can use the FT Raman. FT Raman has advantage that it uses the laser as 1064 nanometer laser, and it is a fluorescence free laser, so you can use it very nicely for analysis of your sample. Now, this is the one of the studies of bee breeds from eastern Ukraine. So bee breads is typically, these are the pollens that are collected by bees from the plants and stored in the comb. So that is their food. So it's called bee bread. Well, this is considered to be, and what we get it from that comb is that honey. It's considered to be the food supplement for nutrients. And the chemical composition of this bee bread is depends on this what kind of pollen the flower has, and it varies from species, also the geographic area and collection time. So they wanted to understand what kind of components that are there in the particular pollen, so that finally what kind of output they will get when it is taken by the bee and converted into into the honey or the material in their combs. So they use both. Now, this is a very good example of how these Raman as well as IR spectra can be used to understand the material. Now, both Raman and IR spectra were taken. Our Raman spectra was taken with the FT Raman module with Nicholas IS-50. So you can see here when they have chosen 5 different types of pollens from different materials, and try to identify what kind of composition is present. So depending on the absorption of particular peak, they have different types of carbohydrates, different types of proteins, and different types of different types of kind of an aromatic compounds like lignins or lipids are there in their molecules in their chemical composition. Raman spectra, Raman gives you the similar information, but as I said earlier, it gives you the peaks which are not so strong in the Raman, in the IR. So here you can see that the carotenoid double bonds, which you see, are there strongly absorbed in the Raman spectrum. And this is how sample number 3 and sample number 1 they have some amount of the carotenoid proteins carotene in their so this is how so it can be used as a chemical markers for a botanical origin that the specific pollens like sunflower contain this compound. So if you get a material for say from the market, and you want to understand what is the source of that material, well, by understanding the peaks that are there, you can identify the source. It can be used if you see the peak as this peak of at around say 1180. Well, then it indicates that it is from sunflower kind of component, or sunflower. The origin is from the sunflower. So this is how, and also these are the bands. As I said, the physical or polymorphic structures can be identified by the Raman. Here it shows that these are the peaks, which are you see several peaks in this region, which indicates that there is a presence of amorphous fructose is there in your sample. Well, these are the examples which I've chosen in order to show the capability of Raman spectroscopy in the food industry. But as I said earlier, it is not limited to one of the industries. It has been used extensively in various industries, from catalysts, from polymers, from pharmaceuticals, and for forensic and other fields as well. Now, this is the typical example what we use in the pharmaceutical industry. So, for example, if you get a tablet from the innovator drug, and as a company, you want to understand what is the composition of that tablet. Well, Raman spectroscopy help you in this one. So you can choose a region of that tablet under the microscope, and then do the Raman analysis, and will understand how much aspirin, how much acetophenone. It has the API like aspirin, acetophenone, caffeine, and titanium oxide majorly present in this tablet. And you can see here, this is how you can have the composition of your sample under the microscope. When you do the analysis, you will understand how much where it is located, how is it distributed, how much is the composition of that particular material, and you can then replicate that sample. So here they have used the Raman imaging, so because of which it has been done around 2,29,000 spectra were taken in a very short time, and you can produce this spectra, and in a very short time you can do the analysis of your sample. So it has a very high spatial resolution. So very small sample area, around 5 micron, for around 500 microns. Sorry, 100. Yeah, 225 by 250 micron have been analyzed in a very short period of time. Well, it has been also used for, as I said, for the biological analysis, even if it is it's an aqueous solution. Here is an example of an algae samples which have shown the fluorescence. Here is they use earlier the 532, which shows a strong fluorescence. So they have to go to the higher wavelength laser, that is 785 and 785. You can see a nice spectrum of the algae samples with no fluorescence at all. And from the intensity of peaks from 1650 to 1440, you can understand the number of double bonds, carbon-carbon double bonds that are present in your in the lipid that are there in that algae sample. So from this, they have identified that A, B, C different samples have different numbers of carbon-carbon double bond in the samples of the lipid. This is another example of the how it can be used for biological samples. Here is to differentiate the cancerous cells. Now, when you have cytochrome C, that is localized in mitochondria. So when you have a normal cell present in your molecule in your body, then this cytochrome C has been localized in mitochondria and not around all over the cell. But when your cell becomes cancerous, what it shows is that the mitochondria is then, the cytochrome C is then present all over the cell. So this is how by seeing the cells under the microscope using Raman microscopy, you can see whether there is a cancerous cells that are present or not. So you can see here, this is the cell where the cytochrome C has been there all over the cell, inside all over the cell, while here it is present only in mitochondria. So this is how Raman spectroscopy can be also used for this analysis of this cancerous cells as well. So there are different type of applications that are possible. You can do a point and shoot analysis under the microscope, or you can have the imaging, sorry, using the microscope. Very good technique for variety of components, whether inorganic, organics, different types of fields it has been used. Importantly, there is no sample preparation. You can have samples, you can do the analysis sample through the glass, plastics, or water, and you can get the new information about whether there is a physical strain, or you want to understand the orientation of your molecule, any physical change, transformation. All these information you can get using Raman spectroscopy. So with this, I really thank you for your kind attention. And if there are any questions, I can take the questions.
Yeah,
So thank you very
thank
much.
you very much, Dr. Dilip Rawat, for your excellent information shared, maybe due to the experience which you have in the field of analytical equipment, various analytical equipment, and especially in the Raman as well as the FTIR and other spectroscopy. Thank you very much, Dr. Dilip. So, with your
Thanks, sir.
permission, yeah. So, shall we start the question and answer session? If you
Sure, sir. Sure, sir.
comfortable,
Sure, sir.
yeah. Uh, okay. So, is there any difference in the sample while selecting laser for Raman analysis?
No. As I said, when the Raman spectrum is independent of the laser that you use. It will be the same spectrum, same absorption peaks. It will appear whether you use 532 nanometer laser or you use 785 nanometer laser. You choose the laser, you select the laser on the basis of whether there is a fluorescence in your molecule. If there is a fluorescence, you have to go to the higher wavelength lasers. Otherwise, 532 is good. As I said, the efficiency is inversely proportional to the wavelength. Higher the wavelength, lower is the efficiency. You will see less intense peak with 785, higher intense peak with 532. But 532 can lead to a fluorescence, while 785 you may not end up into a fluorescence. And this is how you choose the laser. It doesn't, there is no sample. It is not sample selective. It is the samples. It is in that term. It is sample selective. It gives the fluorescence.
Okay. You mean to say is there are different lasers like 532, 785, even 430. Am I right?
Yeah, 455, 633.
Yeah, 455, 630. So it is not going to differentiate any effect on the sample?
Effect on the sample, in a sense, it all depends on the when you're doing that. This is very critical actually. When you're doing a Raman analysis, there is certain thing called as there is a possibility of burning of sample that is possible. So you have to choose the laser intensity that is falling upon your sample. So when you're going to do the analysis, when you see the experimental setup, you will see the laser power at the sample. And that laser power at the sample is very crucial, because if you increase too much, then it can even burn your sample. So there's a possibility that the point at which you are focusing on, it can burn your sample if you have a more laser power. So you start from the less laser power and then increase it till it doesn't burn, or it doesn't lead to heating, or it doesn't lead to fluorescence. Because you need more intensity as well, then you have a more intense peak. But this is the compromise. You always have to do that compromise, see what is happening to your sample, and particular laser power you choose depending on depending on your sample.
Okay, so we have to choose a laser depending upon the sample. Is it?
Yes, depending on some sample melts, some sample they get decomposed with. It's a higher. The intensity of laser is very high.
Okay.
For some samples, like if it's a very solid sample, like inorganic samples, it may withstand at more laser energy, while some organic samples may withstand less energy. So then that is why you have to choose the particular laser power. And then there is a slit, pinholes you can change to increase the pinholes can increase the amount of light that falls upon your sample. You can have a 25 or you can have a 50 kind of a pinholes, and then you can you have that different types of options. What you have to see is it doesn't lead to sample heating and sample decomposition. Till that, you can increase the laser power till its maximum you can go for a particular laser.
Okay, how to determine the unknown samples?
Uh, it's a similar to what you do in infrared spectroscopy.
Okay.
You see the particular peak has a particular vibration leads to a particular absorption in the Raman spectrum, and then you can correlate that information and then understand what kind of unknown material it is, or you can have a laboratory search.
Yeah, that is next alternative. So is it possible to detect
Yes.
intracellular pigments in microorganisms?
Yes, it is possible, but then you have to do the you can refer more literature about it, how they do it, depending on what kind of sample it is, organism it is. You have to use different lasers and different combinations. But yeah, it is possible.
Yeah, so even though it may be a leaf or microorganisms, you start with low wavelength, then you can go for increasing because we have to see the sample also.
Yes,
Yeah,
depending on the sample. Yeah.
correct. For leaf sample analysis in Raman spectroscopy, any preparation method should be followed, or as like we can keep in the FTIR leaf or
No, no need. No need. As I said, no sample preparation. It is just a laser light falls upon it, so no actual contact happens. You just keep the leaf sample under your microscope, focus on the particular sample, and then do the analysis. There's no need. Not much. If there is a typical anything else, to understand a particular component, if certain things has to be done, then you can do it. Otherwise, there's no need.
okay. I think Dr. Amruta has raised her hand. So, Dr. Amruta, madam, can you unmute yourself? If you want to talk to Dr. Dilip before going to the next question. If you have any doubt, yeah. Madam, if you have any doubt, madam, you can unmute yourself. Yeah, please. Yes, madam.
Yes, ma'am.
Wonderful, wonderful. There are some microorganisms which are having intracellular fluorescent pigments. Intracellular fluorescent pigments which are of significant in anti-cancer therapy, anti-cancer treatment, like the chloroxanthomycin, etc. Sometimes they have intracellular fluorescent pigments.
Fluorescent.
There are certain microorganisms which are having orange fluorescent or yellow fluorescent pigment.
Well, then you have to go to the higher wavelength region, madam.
Want those pigments with Raman microscope.
I'm sorry, ma'am. Actually, I couldn't hear you complete question properly.
Okay, Dilip, I'll just interact.
Sir,
Madam,
if you have,
yeah, madam, your voice is not audible. Number one. Number two.
Now, is it audible?
Yes, madam. Please.
Now, yes, ma'am.
There are certain microorganisms which have fluorescent intracellular pigment which fluoresce orange color or yellow color. Those pigments have greater significance in cancer therapy and antioxidant pigments. Is it possible to quantify those pigments in Raman spectroscopy? As you said that there is an interference of fluorescence with spectra Raman.
Absolutely, ma'am. So if there is a fluorescence, it is difficult to take Raman spectrum. So you have to. The only option is you can change the lasers, and there are some options by which you can decrease the fluorescence. So you for a particular sample, you have to may have to do some literature search and understand how you can suppress the fluorescence. And then it is possible to do that analysis. Otherwise, Raman may not be a good technique to do the analysis of these kind of material. You need to have some, suppressants of fluorescence. There are some techniques. You have some saturations to be done. you saturate the fluorescent signal and then take it out, or you can, as I said, you can go to the longer wavelength lasers, but then you have to check it, and then only then, or maybe literature can help you in this aspect. Not a good answer as far as particular this subject is concerned.
Because the fluorescent pigment shifting from longer wavelength to shorter wavelength, automatically they are not exhibiting the fluorescence. What I feel.
Yes. Yeah. So once you have, maybe you can try 785 nanometer laser and check it, or you can go to 1064 laser and check the whether it gives you a Raman spectrum. If it gives you a Raman spectrum, maybe then you can quantify it.
And I understand the essence of your answer. So,
Yeah.
Okay, madam. Thank you very much. I have sent Dilip, his contact details, dilip.raut@thermofisher.com. So you can
Yes.
write. Yeah, you can write.
Then
Yeah, definitely he can help you even in more. Thank you, madam. Thank you very much for your interaction on this afternoon session. Yeah, Dilip, shall we continue the question and answer?
Yes, please.
Yeah. Could Raman spectroscopy be used to test fabric coated with nano finish? What results could be seen?
Well, it can be used. What results means? Well, you understand what is there on the in that fabric, what kind of composition is there, and how it is interaction. If there is an interaction of nanomaterial with the fabric, so that kind of material, that kind of information, you can get it from that.
Yeah. So, what is the difference between Stoke and anti-Stoke scattering and Rayleigh scattering?
So as I showed in my, in that basic, when I was talking about the basics, that when the laser light interacts with the molecule, it falls upon the molecule. Molecules goes to the virtual state. So it absorbs that complete photon, goes to the virtual state, and then when it relaxes, it comes back to the ground state. So it comes, if it started from V0 state of the electronic state, ground electronic state, it goes to the virtual state, come back to the V0 of the E0 electronic state. That means it completely gives away that photon energy, and that is what we call as Rayleigh scattering. While in some cases, one out of a million times, what happens is that when it coming down from the virtual state, it, rather than going to V0, it comes to V1, and the molecule absorbs the energy of that particular vibrational state, V0 to V1. So that difference, it has been absorbed. And this is how it shows the Raman spectrum. That is what we called as a Stoke scattering. While sometimes what happens now, as you know, that there are some molecules are always at the higher energy state. So there are some molecules, most of the molecules will be at V0, but there are some molecules will be already present at V1. Now, when V1, the molecule in the V1 absorbs the same photon energy, is go to the higher virtual state energy. And then when it comes down directly to the V0 state. And there, that is what that kind of an absorption is called as an anti-Stoke. So that is the difference between the three. So what mainly you see, no change is basically the Rayleigh, which is the most predominant thing that has happened in the scattering of light, and then Stoke and anti-Stokes.
Again, related to the same question, what is virtual state? As I know, only ground and excited state.
Yeah, so this is that's why it is called as a virtual state. So it's something which is
it is virtually
something neither virtual state. So what happens is it's like you completely taken that photon energy and goes to a state, just an absorption. It is not related to any of the, so molecule has a typical electronic states, is that's typical vibrational states, which are defined states for every molecule. But there is, you give an energy, I completely take it fully, and that is we called as a virtual state. And then typically that happens in the Raman effect.
Okay.
So there's clear cut. This we call virtual state.
Okay. Can we change vibrational mode of molecular or make it Raman inactive to Raman active, or vice versa, by focusing IR laser light?
No. That is typical to a particular molecule, whether he likes to absorb an iron or Raman. It depends on, as I said, there are rules that are defined. If it is change in the dipole moment, it will absorb. If it is polarizability change, it will show a Raman absorption in the Raman. You can't just change it like that. It's an inherent property of the molecule.
Correct. What is the difference between Raman and IR spectroscopy?
So as I mentioned in one of my slide, IR spectroscopy is all about the absorption spectroscopy. IR light of a particular vibration energy, if it matches, it absorbs light and it transmits the rest of the light. Raman, on the other hand, is a scattering technique, is a scattering phenomena. Molecule light falls upon the sample, it scatters the light in terms of Rayleigh scattering, Stokes scattering, anti-Stokes scattering, and then it shows the Raman effect. So this is the typical difference. But what you see is the same thing, vibrational change, and therefore they are part of the vibrational spectroscopy.
Okay, how we can measure the gas concentration in absorbent materials using Raman spectroscopy?
Yes, if it is adsorbed, then we can do. So it will have its typical, absorption peaks. And then, by understanding how much it is absorption and correlating with, so because it is similar to your Beer's law, the intensity is directly proportional to the concentration. So by, knowing the peak of the particular adsorbed gas, you can correlate it with the concentration.
Correct. So how can we perform Raman spectroscopy of thin film coated on glass substrate?
Yes, we can. Yes, we can. So we have to place that glass film under the microscope and focus the Raman light on the top of the film, and then you can do the analysis.
Correct. Okay. I think I have done almost all the questions, even in chat box of both YouTube as well as in the my personal private chat box also, from the Zoom chat box. So if you have anybody wants to talk to Dr. Dilip, or if you want to ask any questions, even I just shared his contact details. Even in the last slide also he has given his contact details. Okay, there will be another question. Okay, so we'll take another 2 or 3 questions because almost we are running out of time. Let me see. Okay, how we can measure the gas concentration in absorbed materials using Raman? I think we already. Yeah. How rice silicon is useful in making coating material?
Rice. Well, well, I don't have expertise in this one. How they prepare it. Well, to be frank, I have no idea.
Okay.
How the rice silicon is useful for making coating material.
How to determine G and B band in graphene?
Yeah, so basically, when you're looking at graphene, the graphene, if there is no defects, then you see this 2D and G band, and if you have that, if you have defects, you see that D band. So this particular bands can be useful for you to understand whether there is a mono layer or whether there is multi-layer graphene is present or carbon nanotubes. These are the carbon materials which absorbs and it gives you very nice bands in Raman spectroscopy, and very useful by that different by understanding the ratio of intensities between this D band and the G band. You can understand what is the layer, what are the layers that are there in graphene. So it's a good technique. Yeah, absolutely. So if there is a D band, there is a defect that is there. So there are different information you can get it from this.
Okay, so I think we have done almost all the questions, even in the chat box as well as because one of the participants reminded. So there is a cube that was a graphene. So we have cleared that. Yeah. So I think we have. Thanks for the reminder also from the participants. I think we have done all the question and answer session. If anybody having any clarifications, please have a contact to the Dr. Dilip. Definitely he will help you without any interest, because he is having almost 12 to 13 years of experience in the field of spectroscopy. Okay, so on behalf of the organizers or on behalf of the all the participants who was patiently listening in the afternoon session, that to the time which is a very tough task to make it. Even almost 1 hour 40 minutes, it's 100 minutes he has non-stoply explained about the Raman spectroscopy and made you guys to active in this afternoon session. And on behalf of all of you and on behalf of University and Center for Nanotechnology, I extend my sincere thanks to Dr. Dilip for his wonderful presentation. And also I should take this opportunity to thank our Thermo Fisher team. So
Yes.
really, they have done, wonderful team, and made, because of them, all and all their coordination, I can say all the analytical part, it may be FTIR, it may be Raman, and even we covered the XPS. Really, all the things has been, even initially we covered with the UV. So all the team, I should say thanks to Thermo Fisher team, and my personal thanks to the Arun, because he has connected all the members
Yes.
for this particular webinar. Even today also he came here for our demo. So I thanks to Arun, I thanks to whole Thermo team on behalf of the participants and on behalf of the all of you, because the next will be Thermo team or different Thermo team, because the next team is they are going to explain on LCMS, GCMS, SCPMS, and this team is different, and present what we are dealing, this team is different. Okay, so I'm not going to take too much of time. So on behalf of the all the once again, on behalf of the organizers and all my participants, I extend sincere thanks to Dr. Dilip. So if it is anything comes from the uh, our participants, definitely I will forward with you. Kindly help them for their question and
Sure, sir.
answer session. Okay, so thank you very much, Dr. Dilip.
Yeah, yeah. Thank you. Thanks a lot, sir. Thanks for this opportunity so that we can, present this technology. And thank you very much. Stay safe. Take care, sir.
Yeah. So this is the information to our fellow participants for the tomorrow session. So we are entering to the ninth day for tomorrow. So we have two sessions as usual in the morning as well as in the afternoon. In the morning, we have a Dr. R. Parthasarathi, Deputy Director, Directorate of Research and Development, Annamala University, Chidambaram. So he is going to deliver on synthesis and stabilization of silver nanoparticles using biosurfactant and its applications in the field of antimicrobial, and he did a couple of experiments on textiles also. So it is a wonderful, and they have done a lot of patents on this particular biosurfactants by using the silver nanoparticles. So I request all the participants, please join with us at sharp 10:50 so that we can start our session by sharp 11 o'clock. And in the afternoon session, we have Dr. Vijay Joshi. So he's from LabLine Mumbai. So he's going to deliver or going to explain on TEM, tunnel electron microscope. So and its different applications. So please join with us for the both the session in the morning at 10:50, in the afternoon at 2:50, without without mistake or without delay in the joining in the session. So once again, I extend sincere thanks to all the participants and all the speakers and those who have done the wonderful job for this 10 days webinar on role of nanotechnology in food and agriculture. Thank you one and all. Jai Hind, stay home, be safe. Thank you.